I want you to try something. Grab a piece of paper and write down the exact value of pi. Or, if you prefer to, try writing down the exact value of the square root of 2. Go ahead. You can't do it. No one can. Because the sequence of digits for those numbers never ends, and it never settles into a predictable pattern. Even if you fed this task to the largest, most powerful mainframe computers ever built, they would calculate forever, without ever reaching the final digit. To understand why, we have to look at the apartment building where numbers we use every day live. This is the world of real numbers. This building is divided into 2 distinct neighborhoods. One side is highly organized and predictable, the other is completely wild. Understanding how these numbers behave allows us to map out the logic behind our number system. Let's start in the organized neighborhood, the rational numbers. These numbers are defined by their predictability. You can tell a number is rational if it passes a simple test. It can be written as a fraction of 2 integers, an a over a b. Take the whole number 5. It fits perfectly into 5 over 1, or a decimal like 0.75, which translates cleanly into 3/4. This also includes repeating decimals. A number like 0.666 might go on forever, but it follows a clear rule. Because that pattern is predictable, we can contain it. We can write 0.666 as the exact fraction 2/3, making it rational. As long as a decimal either stops or enters a repeating loop, it belongs in the rational category. Square roots are where things get tricky. Is a number like the square root of 9 rational or irrational? Since 9 is a perfect square, its root is exactly 3. Because 3 can be expressed as a fraction, the square root of 9 is rational. But if we look at the square root of 2, we leave the organized neighborhood and enter the irrational one. 2 is not a perfect square. When you calculate its root, the decimal never stops and it never repeats. There is no pattern to find here. This number cannot be written as a simple fraction, no matter how many digits you calculate. This is why pi is the most famous irrational number. Its digits run on forever, without any repeating cycle to hold them together. Irrationality is a property of any number that simply refuses to be contained by a ratio. The difference between these 2 worlds isn't about how long the number is, but how it functions. You can use the 2-second test to instantly classify any number you encounter. Does the decimal stop? Does it repeat a pattern? Is it the square root of a perfect square? If the answer to any of those is yes, the number is rational. But if the number runs forever without any pattern at all, it's irrational. Now, a new number isn't just a symbol. You see how it behaves, either as something neat and predictable or truly wild.
Imagine building a square picture frame. You need to cut a diagonal support brace, and the math says the exact length is the square root of 2 meters. But look closely at your measuring tape. It only shows marks down to the millimeters. You cannot cut a piece of wood that is infinitely precise. So here is the real problem. If the square root of 2 goes on forever, and you can never write it exactly, how do you figure out exactly where it sits on a physical ruler? Last time, we saw that rational numbers can be written as neat fractions. Irrational numbers, like the square root of 2 and pi, go on forever with no repeating pattern. To find them, you play a game of hot and cold. Think of the number line as a dark room. Your first guess narrows the search to a broad region. Your next guess gets warmer. You keep zooming in until you know almost exactly where it is. You don't need the exact infinite number to pin down its precise location on a scale. You just need a system to box it in. That system takes 4 steps. First, you find the bounding perfect squares. Second, you identify the bounding whole numbers. Third, you test the tenths. And fourth, you test the hundredths. The entire process relies on step 1. To do it quickly, you need to memorize the standard 8th grade perfect squares table. This table shows the perfect squares that act as your permanent landmarks. You will use them to navigate the number line for every problem we tackle today. This horizontal number line maps our first problem. Let's find the square root of 2. For steps 1 and 2, we check our landmarks. The number 2 sits directly between the perfect squares 1 and 4. That means the square root of 2 must lie right here, between the whole numbers 1 and 2. Step 3 zooms into the tenths. We test the decimals. 1.4 squared gets us 1.96. 1.5 squared is 2.25. Our target,
2 is wedged right between those results, narrowing our location to the space between 1.4 and 1.5.
For step 4, we test the hundredths. 1.41 squared is 1.9881. 1.42 squared goes over at 2.0164. Our best estimate for the square root of 2 is 1.41. Once you know the steps, you can move much faster. Take the square root of 10. 10 is between the perfect squares 9 and 16, putting our target between the whole numbers 3 and 4. This new zoomed-in number line shows the result of skipping straight through the decimal testing. 3.1 and 3.2 bracket the target. Zooming further, 3.16 squared gets us 9.9856, and 3.17 squared crosses the 10 mark. Our best estimate lands exactly at 3.16. This process of manual zooming is the exact logic your calculator uses to spit out the decimal places for any square root. Now look at the square root of 28. Because 28 looks close to 25, you might guess it rounds cleanly to 5. Don't fall into the visual guessing trap. Always test the decimals. This zoomed-in number line proves why. 5.2 squared equals 27.04. That shows the true location is actually much further up the line, sitting between 5.2 and 5.3. Zooming to the hundredths, and 5.29 squared is 27.9841. The real estimate isn't 5 at all, it's 5.29. Keep in mind, this perfect square method only works for square roots. Pi is the famous exception. This number line spans from 3 to 4 to show where it lives. You just need to memorize its rough address. Pi is approximately 3.14159, meaning it sits just past 3.14, a little closer to the 3. The rule holds. When dealing with irrational numbers, mathematical testing always beats your visual intuition. The highest level application of this method is comparing irrational numbers to rational ones on a test. You never need the exact endless value. You only need a solid decimal estimate. Let's try an example. Which number is larger, the square root of 50 or 7.5? This number line compares the two values. Apply the zoom method to 50. 7.0 squared is 49, and 7.1 squared is 50.41. That drops the square root of 50 at an estimate of 7.07, visually proving that 7.5 is the larger number. Now let's try a multi-number challenge. Order these three from least to greatest: the square root of 3, 2, and the square root of 8. Finding the decimal estimates handles the hard work. The estimate for the square root of 3 is 1.73. The whole number 2 stays exactly 2.00, and the estimate for the square root of 8 is 2.83. Converting every term in the problem into a common decimal estimate makes comparing them foolproof. Pause the video and test your zooming skills on these three problems. Unpause when you are ready to check your work. This number line tracks our answers. For question 1, the square root of 40 sits between 6 and 7. Zooming into the tenths gives us an estimate of 6.3. For question 2, testing the perfect squares shows the square root of 17 is roughly 4.12. That makes 4.5 the larger number. And for question 3, the decimal estimates organize the line. The square root of 5 at 2.24, then 2.5, then the square root of 10 at 3.16. You can now map endless irrational numbers onto a physical line with confidence. Next up, we leave numbers entirely and grab the power tools of algebra, where you will learn to simplify huge exponent expressions in seconds. Say next when you are ready for topic 3.